All right, so now we're going to talk about section 9.4, rare events. So we're going to talk about this in such a way that I think it's going to work better if we think about the null hypothesis as being our assumption, and that rare events are such that we're going to have, they're not very likely to happen. So this example in the center is going to work really nicely. So going to the birthday party of a wealthy friend, and they grab the prize, and we're going to be blindfolded. That means it's going to be a random sample, and we have 200 plastic bubbles. And we've been told that there is one that has a $100 bill, and that the Dolly's the first one to choose, and she gets it. Lo and behold, she gets the $100 bill. And the random chance of that happening is 1 out of 200, or 0.005. Okay, not very likely, really highly unlikely. So she's thinking that maybe they were told wrong, that maybe there are more $100 bills in the basket. So when a rare event like this occurs, it makes us doubt the assumption, or doubt that what she was told was $100 bills being in the basket. Okay, now we're going to go to how to use the sample to test the null hypothesis. So we're going to introduce this idea of the p-value. And the p-value is the probability that if the null hypothesis is true, the result from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. Okay? So it's if the hypothesis is true, that the results are going to be coming from chance. So the probability that random chance will give us a more extreme value. All right, so now when we take a look at this, if we have a large p-value, that indicates that we should reject the null hypothesis. Okay. A smaller p-value tells us that the more unlikely outcome, and there's stronger evidence against the null hypothesis, which would cause us so that we would then reject the null hypothesis. Okay. That means we have enough evidence. All right, so when we take a look at the drawing of this, we have our observed data point, and our p-value that's the area above that, and that's the probability that it's going to be more extreme or more unlikely. Okay, so we can have them on the right for this p-value. We can also have them on the left, or we can have them on the left and the right. So you can have them split. So we can have a left, a right, or left and right. Now the examples, as we go to section 9.5, we're going to go through all of these. So the first one we're going to talk about in a hypothesis test problem is the level of significance. This is our alpha. Okay? It's preconceived and it is preset. You do this before you collect your sample. So make sure that you're doing this before collecting your sample data. Okay? And if no level of significance is given, the common standard to use is 5%, or 0.05. Now, quick reminder that the alpha is the probability that a type 1 error will occur. Now, this happens when the null is said to be true. So the alpha is the probability that if the hypothesis is true, we make that specific error. Okay? And we use the 0.05 for a 5% if nothing's given. And now we're going to draw the picture. You can have the left or on the right, or split evenly between the two tails. Okay, so left, right, or two-tailed. And for our alternative hypothesis, that's tested on the right, left, and that's how we know. So the alternative hypothesis tells us what kind it's going to be. And remember that the alternative hypothesis never has the equal sign. All right, now remember that we're going to take our p-value and compare it to our alpha. That's going to help us decide whether to reject the null or to fail to reject the null. All right, so if we take a look at this one, our null hypothesis tells us that the mean is going to be equal to 5, and the alternative hypothesis that h sub a is going to be less than 5. Okay, so our null is equal to 5 and the alternative is less than 5. So that makes it left-tailed. So it's going to be on the left side. All right, so now example 9.12. We're looking at it being less than or equal to 0.2. So our null hypothesis is less than or equal to 0.2, and the alternative is greater than 0.2. So that means it's going to be a right-tailed because it is greater than. So right-tailed because it's greater than. So example 9.1.3, we have equal to 50 or not equal to 50. So our null hypothesis is equal to 50, and the alternative is not equal. So that means it's going to be two-tailed, so it can be on either side, and it gets evenly split between the right side and the left side. Okay, now if we look at example 9.14. So this is talking about Jeffrey the swimmer. He established the mean time of 16.43 seconds for swimming the 25-yard freestyle with a standard deviation of 0.8 seconds. His dad buys him some goggles, and he thinks these goggles are going to help him swim faster. So they do 15 trials of that same swim, the 25-yard freestyle swim, so 15 different swims. And his mean was 16 seconds. So Frank thought the goggles helped Jeffrey swim faster than the 16.43 seconds that he had previously. We're going to conduct a hypothesis test using the level of significance at 5% or 0.05. Okay? And we're going to assume that it's normally distributed. So our null hypothesis is going to be saying that it was equal to that same mean. In other words, that the goggles had no effect on his swimming. So mu is equal to 16.43. And the alternative hypothesis, so that's going to be the same and because it's from his first swim without the goggles. And then our alternative hypothesis saying that it made him faster, so that it is less than 16.43 seconds. So having that less than just means that it's going to have him swim faster, and it makes this left-tailed. Okay, so it's going to make this left-tailed. Now if we take a look at our flow chart, we have the hypothesis test for the mean, and now we take a look and see if we know our standard deviation. We do know our standard deviation because it's for the same swimmer. This is not from a lot of different swimmers. So we know the standard deviation for this one swimmer. And once we know that, then we need to go and do our required check. Okay. With this required check, down here on the bottom, you need to have the random sample and be normally distributed, or have the n be greater than or equal to 30. So on this one, we know that it's random sampled and normally distributed. It said that in the question. So that tells us we're going to use a z-test. So on your calculator, we're going to go to stats and then test, and we're going to use the z-test. Sorry about that. So once you get into the z-test, we're going to use statistics, and we've got the 16.43 as our mu, and then the 0.8 is the standard deviation. Then we look at the sample, that's the 16, and he did 15 different swims. And this is going to be, we're going to say that his second swim was lower than the first one. So we go through and then we come down here to calculate, and that tells us that the p-value is 0.01868. All right, so now we know that that's going to be on the left side. So that's our p-value because it's 0.0187, and that's actual level of significance. Okay, so once we have that p-value, that's the actual level of significance. And This is interpreted as if the null was true, that's 1.87% probability that this change is due to random chance. Okay, that's really small. That's a rare event. So we're going to compare our values. We're going to compare our alpha at 0.05 and compare it to the p-value of 0.0187. And you can see that the p-value is lower than the alpha value. So if p is low, the null must go. So if p is lower than the alpha, we need to reject the null hypothesis. All right, so I just used a mnemonic there to help us figure this out. If the p-value is lower, the null must go. So if p-value is low, the null must go. That means p-value is lower than the alpha, we reject the null hypothesis. If the p-value is high, the null must fly. If the p-value is greater than the alpha, then we fail to reject the null, or we do not reject the null. Okay, so if we make this decision, this is once again just another spot. We're going to, if p is low, the null must go. That means that there is significant evidence to conclude that the null hypothesis is incorrect. Okay, and the alternative hypothesis may be correct. All right, that just may be correct. So we just don't have significant enough evidence. If the p-value is greater than, or the p-value is high, the null must fly. So we do not reject the null hypothesis. That means there is not significant or sufficient evidence to conclude that the alternative hypothesis may, so the alternative hypothesis may be correct. Okay, our data is just not significant. So when you don't reject, it doesn't mean that it's not true. It simply means that we didn't have enough data to provide sufficient evidence to cast serious doubt on the truthfulness of the null hypothesis. All right, so at the 5% significance level, we concluded that Jeffrey swims faster using the new goggles. Okay, the sample data show that there is sufficient evidence that Jeffrey's mean time to swim the 25-yard freestyle is less than 16.43 seconds. Okay, in other words, the goggles helped. All right, so when the p-value is lower, we rejected the null hypothesis. We rejected that it was equal to the 16.43 seconds. All right, so it made him faster. Example number 9.15. A college football coach thought that his players could bench press a mean weight of 275 pounds. Okay. So we know the standard deviation to be 55 pounds, and the players thought they could lift more. So they asked 30 of the teammates to bench press and say what their bench press maximums would be. And they ranged, and then they gave the they gave their mean in different values. So we have all those data points, but they're given in such a way that we have the weight and then how many lifted that. So the weight, how many lifted, the weight, how many lifted that. All right, so we're going to put these in our calculator as a list. That'll be our list 1 is the actual weight amount, and list 2 is our frequency, how many people lifted that weight. And we're going to do a test using a 2.5% level of significance for our alpha. So that determine the bench press is more than 275 pounds. So we set up our null hypothesis. Our null hypothesis on this one is going to be equal to the 275 pounds. That's what the coach believes. He believes that they can lift a mean of 275 pounds. The players think that they can lift more. So the alternative is going to be greater than 275 pounds. That makes this a right-tailed test. Okay. Now we have the hypothesis test, and we know it's going to be mean, and we know the standard deviation, and we go through and do our required check. And for this one, it's a random sample, and we have n is equal to 30, so it meets that second part. So n is equal to 30. So we passed our required checks. So that tells us that we're going to use the z-test. All right, so you go to your calculator, and on your calculator, you're going to go to your list, and I've already entered this in. My list 1 are all the weights. List 2 are the frequencies, or the number of players that said they could lift that amount. So list 1 is the weight, list 2 is our frequency. Now we're going to go to our test, and we're going to do the z-test, and we're going to take this one from the data because we're getting it from our lists. So our mu is the 275, and our standard deviation is the 55. And then we have our list of the weights is list 1, and our frequency is list 2. And they thought that they could lift more than that, so this is right-tailed. And then we're going to go down here to calculate. And we have our p-value as 0.1330599. So our p-value is calculated. Now when we draw this, it's going to be a right tail, and our p-value is 0.1323, and it's going to be to the right of that because it's more than. Okay, so now we need to say how we are going to interpret that. So we've got 13% by chance that they would have lifted more than that amount. Okay, so just by chance. Now we need to compare our alpha, excuse me, our alpha with our p-value to help us to make our decision. So our alpha, in this case, we did a 2.5% level of significance, and so that's 0.025, and our p-value is 0.1323. So the p-value is higher than the alpha. So if p is high, the null must fly. So that leads us, do not reject the null hypothesis. So we fail to reject the null hypothesis. And for our interpretation on this, at a 2.5% level of significance from the sample data, there is not sufficient evidence to conclude that the true mean weight lifted is more than 275 pounds. Okay, so there's not sufficient evidence to conclude that they actually can lift more because we did not reject the null hypothesis. So when you take a look at that pound, like the 275 pounds, we just didn't have enough evidence. All right, so now we're going to do example 9.17. June believes that 50% of first-time brides in the United States are younger than their grooms. She performs a hypothesis test, and the percentage is the same or different from 50%. So same or different. That means that this is going to be a two-tailed hypothesis test because it's either going to be equal to that or different than the 50%. So she samples 100 first-time brides and finds that 53 reply that they are younger than their grooms. Okay, she wants to do the test with 1% level of significance. All right, so the hypothesis, the null hypothesis, says that the proportion is going to be 50%. It's equal to 50%. The alternative hypothesis is not equal to 50%. Okay, that comes from, it can be higher or lower, and makes it two-tailed. So we have our two-tailed test coming from it being either the same or different. Now, if we come to the hypothesis test, now we know that this is going to be a proportion now. It's not about the means, it's not about averages, it's about proportions or percents. We do our required check. So we take a look at the required check and we see that it fits the binomial conditions, the three conditions, and that it has a random sample and that the number of, for the test part, the number of sample times the probability of success is greater than or equal to 5, and the number times the probability of failure is greater than or equal to 5. So P is success, Q is failure, so that leads us to a one proportion z-test. That's what we're going to use on our calculator. So we come to the 1 proportion z-test on our calculator. And our p is going to be 0.5 for our 50%. And there were 53 brides who said yes, they were younger than the groom. And she had sampled 100 brides. And we're doing the not equal to. So this is going to make it two-tailed. There's going to be some on the left and some on the right. So we're going to come down to calculate. And we can see that our p-value is 0.5485. Okay, that gets evenly split between the two tails. So half of it goes onto the right side and half of it on the left. So half on the right, half on the left. So we're just taking that p-value and cutting it in half. All right, so since the a value is less than, that means that our p-value is higher. So if p is high, then our null must fly. So p is greater than the alpha. So we cannot reject the null. We do not reject the null hypothesis. So we fail to reject. And our conclusion says that at 1% level significance, the sample do not show significant evidence to show that the first-time brides are younger than their grooms is different than 50%. So we don't have sufficient evidence.